Volcanic eruptions are a natural geodiversity experiment for us to learn from. So it leads to climate diversity. I think the recent past is the key to the future.
My guest today is Wyss Yim.
I'm a retired professor from the University of Hong Kong. My field is Earth Systems Science. I did my doctorate in Australia, in Tasmania, and I did do some work on volcanic eruptions, how it got involved in the development of placer deposits. But that's a rather old volcanic eruption, leading to the formation of tin deposits and so on. Since returning to Hong Kong, I got interested in the climatic record, especially temperature, rainfall, and sea levels. And during my career, I have collected a lot of interesting information. Unfortunately, I didn't have time to work on it until my retirement. And now I'm following it up, different leads. For example, the satellite records of volcanic eruptions, tracking the clouds around the globe. And that turned out to be particularly interesting to help understand the record rainfall and temperature in Hong Kong. So that's how I got started. A number of things strike out in my mind. We started measuring temperature and rainfall in 1884. And that year turned out to be the coldest mean annual temperature on record. And I already knew from searching Krakatoa erupted in 1883. And we actually have 3 or 4 very cold years to start off with from 1884. And that seems to be the connection. But the really interesting thing is explaining rainfall, which is much more difficult. Our driest year on record is 1963. I remember as a kid in those days, the water rationing. Water is available for 4 hours in 4 days. So most days you can't even have a shower. So, but what's the reason behind this drought year, the driest on record? And I found out that there's a connection with Agung on Bali. This volcano erupted in 1963. And the circulation change influenced by this volcanic eruption led to offshore wind throughout much of the year. And this led to severe droughts. 1982 was another year of interest. It's the second wettest year on record. And I found a paper in Science showing the tracking of the volcanic clouds around the globe. It took 21 days for this cloud to circle around the globe after the eruption from Mexico. And Hong Kong that year was the second wettest on record. So I've been intrigued by that, and I actually started to work on it even before I retired. Then 1991, we were lucky enough to have Pinatubo erupting very close to Hong Kong. And that was also a drought year in spite of the fact that the eruption was in middle of June in 1991. So already 5.5 months have passed, and we still have a relatively dry year, one of the 10th driest year on record. So that led to great interest. And the final straw really convinced me was 2008. That year was the International Year of Planet Earth. I was involved in publicizing the role of earth science in climate change. And I was asked to organize a meeting by the board of directors of the committee, who was visiting Hong Kong at the time. And we had an evening meeting on the 6th of June, 2008. That evening was quite dramatic. We have one of the worst rainstorms in Hong Kong's record. I have been tracking this volcanic eruption in Chitan, in Chile, that year, which was announced in the newspaper. It erupted 1st of May, 2008. And 35 days, roughly 35 days after the eruption cloud arrived in Hong Kong after circling the globe 1.5 times. And it resulted in the worst rainstorm and the wettest June on record in Hong Kong. And that got me rather excited. I started to track the volcanic cloud from Chile across the South Atlantic to South Africa, across the Indian Ocean, and then to Australia, with airports closing in Adelaide and Melbourne, proving that this is the first time around the globe. But the second time around the globe, it crossed the equator because of the timing. May, June is the autumn season, so the sun is crossing the equator. And we had the southwest monsoon event bringing this rainstorm in Hong Kong on the 7th of June, 2008. So that was rather exciting for me. So we actually wrote that up in the chapter of a book, and it was published. Yeah. But my other interest, it was submarine volcanic eruptions. The reason why is I have been involved with an international group of researchers called INQUA, International Union for Quaternary Research. And they are the scientific group already knows something about long-term climate change through interglacial glacial cycles. That is really global change, not short-term changes, a little bit warmer, or a little bit wetter or drier in different regions of the world. That is really not global change, but interglacial glacial cycles are really global change. And this group got me involved in studying sea levels and global carbon cycle. I've always been interested in the oceans because of the continental shelves, the area we can actually dive into to look at interesting things. And one of the exciting things is to look at subaerially exposed continental shelves when sea level was much lower, and what really happened with the carbon cycle. So we basically have different types of continental shelves, and that got me quite interested in carbon cycle. We have muddy shelves, like in the South China Sea. When they were subaerially exposed, we have acid sulfate soils releasing carbon dioxide. And then we have carbonate platforms. For example, the Great Barrier Reef in Australia is a carbonate platform. When sea level was much lower, say 130 meters below the present, all these coral reefs will be subaerially exposed and will be calcified, releasing carbon dioxide. But the continental shelves, when they were exposed during glacial periods, are still highly saline. It's unsuitable for vegetation to grow until the salt is flushed out. And this helps to explain why CO2 lags behind temperature in the ice cores. And this is something we work on with the French group, I think, who are the expert in drilling coral reefs, including Tahiti and so on. So a lot of interesting things. But the most exciting thing was information passed on to me about hot seawater on the surface of different parts of the oceans. I think Benny Peiser told me about the Pacific block, and I followed it up because I remembered I had a paper cutting of a volcano coming up 940 kilometers south of Tokyo called Nishinoshima. And I chased up the information on this, And I thought this may well be the explanation why we have this North Pacific block. It erupted for 2.5 years, initially as a submarine eruption, and then it developed into an island. And there's some subaerial eruption, but there's still submarine volcanic eruptions. And it helps to explain these hot seawater on the sea surface, which may become quite important in regional climate. So there's a lot of very exciting things going on. So I couldn't be bothered in my retirement to publish in top-notch journals. So I took the easy way out. I got a sympathetic editor of the Imperial College magazine, Imperial Engineer, and he's published 12 of my articles on these exciting discoveries of volcanic eruptions. So I think this is my research career extended a little bit, even though I publish in top-notch journal, because I know the difficulty to have a contrary view. One thing maybe I may like to mention is the International Year of Planet Earth. It's a 3-year project of UNESCO, and the purpose of it was to increase awareness of the role of earth science in sustainable development. It's quite a noble cause. I was behind a group pushing climate change. My angle is continental shelves when they were severely exposed. The chairman of the board of directors, Larry Woodford, was kind enough to nominate me at the inaugural Climate Change Communication Prize of the AGU, but I lost out to Gavin Smith. So I think that's my nearest to fame.
I'm curious, how did they let you anywhere near a UNESCO body, given your views against the narrative? It's amazing.
From the IUGS point of view, I'm a geologist. I'm an earth scientist. But my expertise is continental shelves and sea level. So they wanted me to push this direction in the international year. But the carbon cycle, I think, is obviously quite important.
But from my perspective, this is the good old days, 2007 or so. And nowadays, they would never, ever let you near any body like this, would they? Because you're an unbeliever?
You see, most of my presentation I do put down is a contribution to this PAGES project, the Past Global Change. And they have a relevant group called VIX, Volcanic Eruptions Impact on Society. So this is the importance. So many people are looking at volcanoes as an explanation of climate. Volcanic eruptions do contribute to climate diversity, and you see why from this presentation. We'll introduce how volcanic eruptions affect climate. Then I'll talk about recent examples of volcanic eruptions and a number of influences, including ocean heat waves, extreme weather events, the long and strong 2014 to 2016 ENSO, polar sea ice changes, and the 1995 acceleration in sea level rise, which is seen in many parts of the world. Then I'll draw up some conclusions. I'll start off with definitions of climate change. The United Nations definition has some problems because they assume they know what is directly due to human activity. The IPCC, which is an organization funded by the United Nations, has a slightly better definition based on statistics, usually decades or even longer. But because of the pause in temperature rise, all weather changes are now included in climate change. I like the last definition, a product of astronomical forcing, including solar variability and the interaction of the Earth systems. And this is the part most difficult. the air, atmosphere, water, hydrosphere, the plants, living things, biosphere, the frozen earth, cryosphere, the soil, pedosphere, and then the lithosphere, including volcanoes. So it's a lot more complicated than we think. It's not just CO2 from fossil fuel. The order of importance in driving climate, most important first order is the sun, and that's what is called astronomical forcing, the planets. What is truly global climate change are the interglacial glacial cycles, the ice ages, and then the milder periods. The rest are mostly regional change, including monsoons, seasons, even daily changes. Second order importance are the geothermal heat from the lithosphere, and then from below that, the magma. This is what is called plate climatology. And third order are the human-induced changes, including heat generation, water cycle changes, and greenhouse gases. And some people are thinking that CO2 will overtake the sun to become first order. Is this likely? I'll start off with classification of volcanic eruptions. They can be divided into three main types: subaerial or terrestrial, that means on land, switches on hot air followed by cooling, causing a number of influences, which I've listed here. The second main type are the submarine volcanoes on the seafloor, and this causes the seawater to be heated up at the surface because hot water is lower in density, so it forms ocean warming regionally. And of course, there's a mixed eruption. Submarine volcanoes may eventually build to form a new island, and after the island was formed, it becomes subaerial. For example, the Tonga eruption earlier this year from December 2022 to January 2023. The subaerial volcano model is summarized here. The volcano releases ash and aerosols, and this reduces solar radiation, leading to cooling. Warm air also stores more moisture, so water vapor distribution, air pressure changes. This is a picture of the El Chichon volcano in Mexico in 1982. It was shown by satellite to circle the globe in 21 days, and Hong Kong had its second wettest year on record since 1884 because of the influence of the volcanic clouds. Eruption changes normal air circulation, creates clouds, destroys ozone, releases gases such as sulfur dioxide, which is of great importance in solar radiation impact. Cool air stores less moisture, and the impact lasts longer if the volcanic eruption is larger, based on the volume of material released into the atmosphere. The volcanic explosivity index is used to quantify the size of volcanic eruption on land. By the bigger the volume, you see the big red circle is a scale of 8. The Yellowstone eruption 600,000 years ago was thought to be of this scale. The biggest eruption in the last 100 years or so is Pinatubo in 1991. It has a scale of about 5 to 6. So this is the measure based on explosiveness of the volcanic eruption. But in terms of influences on climate, if VEI is 2, already we can see regional impacts on weather detectable. We are fortunate since the late 1970s to have satellites to measure volcanic cloud to track how they are being distributed around the globe. So this is NASA's A-train called Calliope. So we can do profiling of volcanic clouds. So this is what makes flying a lot safer. If there's large quantities of ash from volcanic eruptions in the atmosphere, it can cause jet engines to stall, causing the planes to crash. How does a volcanic cloud influence the atmosphere? The upper part is called the stratosphere. But normally, the jet stream get interfered with because of the height of the volcanic cloud. Now, the Tonga eruption earlier this year reached a height of 58 kilometers. Typhoon clouds reach 12 kilometers. So it's overwhelmed by these volcanic eruptions changing the circulation. It causes the jet stream to change its course, causing it to meander. Volcanic eruptions also brings a lot of water vapor, creating atmospheric rivers in the sky. And this is a picture of one over the west coast of Canada. Because it comes from Hawaii, it's called the Pineapple Express. Of course, we also have submarine volcanoes. 3 examples that I have studied are shown here. One in the North Atlantic, El Hierro. In the Canary Islands, Tonga eruption in 2014 to 2015. So this is an earlier eruption than the one this year. And then one south of Japan, called Nishinoshima, 940 kilometers south of Tokyo. And this is a long-lasting submarine eruption of almost 2.5 years in the North Pacific. The impacts of these submarine eruptions are that it creates warm surface ocean water, mistaken for global warming regionally. Pressure changes, surface wind changes, sea level changes due to the heating up of the water, you have thermal expansion, ocean circulation changes, and even polar sea ice changes, which I'll show later onwards. So basically, we are talking about regional ocean warming. Basaltic magmas are much hotter, so it has a temperature of about 1,200 degrees Celsius. Statistics on submarine volcanoes are summarized in this table. Approximately 1 million, and 75,000 are rising from the seabed by about 1 kilometer, still submerged by the present sea level. Magma output is enormous, 75%, and we have about 5,000 submarine volcanoes which are active. Basaltic magmas are obviously hotter than acidic magma, but acidic magma is much more explosive. So these submarine volcanoes releases geothermal heat during eruptions, changing the normal oceanic circulation and atmospheric circulation. So the ocean warming may lead to ecological changes mistaken for global warming impacts. We are fortunate that from year 2000 onwards, we have started to have oceanic floats measuring temperature and salinity profiles in the oceans. There are now more than 4,000 of these floats, so they are a good way of detecting hot water rising to the surface from submarine volcanic eruptions. So this is a subject that at least Earth scientists should be interested in looking at. These floats are maintained by different countries, mostly the United States, but China also are involved, as well as many other countries. Now, this is a table which is a bit long and difficult to read, but what I've tried to do is, from volcanic eruptions since the year 2010, listed the major climatic impacts. You won't be able to read through it, but this PowerPoint will be available to you later onwards, and you can read through it. It's a combination of terrestrial eruptions, submarine eruptions, and mixed volcanic eruptions. The location of the volcanoes are shown in the second column, and the timing of the eruption and the climatic impacts that we have found out are shown in the last column. And these climatic impacts included polar sea ice changes, which I'll show in more detail later. Hot seawater patches, the most famous is the North Pacific block as a result of the eruption south of Tokyo, Nishinoshima. Because it's a long-lasting eruption of 2.5 years, the hot seawater lasted much longer and the impact was much greater. Shorter submarine eruptions will have shorter impacts. It may also lead to coral bleaching, also mistaken for global warming. Now, this Iceland eruption, which is difficult to pronounce for most people, I've simplified here to call it E15, 15 letters after the letter E. So this is actually the name of the eruption. It erupted on 14th of April 2010, and it caused major disruption of international flights from Europe to North America. So the brown is actually the cloud, the volcanic clouds. This is the particulates from the volcanic eruption or tephra that may cause the jet engines to fail. People don't realize that this has major impact on extreme rainfall. The weather chart based on satellite analysis is shown here on the 29th of April, 2 weeks after the eruption. And you can see from Iceland, which is located here, a succession of occluded fronts, one after another, penetrating deep into the continental interiors of Europe and Central Asia. And one country along its path, Slovakia, has its wettest year on record since 1818. This is actually the station, Urbanova. The red graph is the temperature, the blue is the rainfall. And you can see that as the rainfall goes to a record high in 2010, it led to cooling of the temperature. So the temperature dropped, showing that the rainfall actually lead to cooling. So this is how moisture is able to penetrate deep into the continental areas. Without volcanic eruptions, this cannot take place. The submarine eruption of El Hierro in the Canary Islands in 2011 to 2012, which erupted for 6 months, led to some notable extreme weather events. The one that affected New York, causing 147 fatalities, is Hurricane Sandy. Estimated damage US $65 billion. And then in the United Kingdom, during 2012, you have the wettest summer in 100 years and the wettest week in the last 50 years in November. So this is a chart of the floods based on treats. So we can see that southwest England around Somerset was severely impacted by flooding that particular year. And this is explained by the warm North Atlantic Ocean, successive frontal activity storm bringing heavy rain to the United Kingdom. In 2014 to 2016, we have one of the longest and strongest ENSO on record. So this is the appearance of hot seawater off the coast of South America. But normally ENSO occurs around Christmas time, but this event is totally different. And I'll go to explain why from these sea surface temperature maps from NOAA. The volcanic eruptions playing a part in this ENSO event, El Niño, are summarized in this table. July 2012, a lot of people don't know this, north of New Zealand there's a submarine volcano called Honorary, and this was the largest deep water silicic eruption of the past century. The pumice raft floating to the surface has a total area of 400 square kilometers. It has 14 vents, and the water depth is from 900 to 1,220 meters. Then in 2013, we have this Nishinoshima eruption south of Tokyo, and this lasted for almost 2.5 years. After a new island was created, it becomes subaerial. 2014 to 2015, Hunga Tonga erupted. So it has erupted 3 times, not just this year. Previously in 2014, 2015, and then another time later onwards. Axial Seamount is in North Pacific Ocean. Wolf Volcano is in Galapagos, and this is a volcano on an island with hot lava flow flowing into the Pacific Ocean, heating up the seawater. Hawaii, Killer Whale was also active. Again, you have basaltic lava flowing into the Pacific Ocean. So you have multiple heat sources to heat up the seawater in the Pacific Ocean. This is a photo from the air of Nishinoshima as it created a new volcanic island. But lava flow continued, and you can see the island building up. So this lasted for almost 2.5 years, heating up the North Pacific Ocean. We have these NOAA sea surface seawater anomaly maps. Nishinoshima is shown here in this red triangle, and because of the circulation in the North Pacific, it forms this hot surface water patch of enormous size, close to the coast of Alaska and Seattle and so on. So this is due to geothermal heat released from the submarine eruption and the change in ocean circulation and atmospheric circulation. In the North Pacific, we have these gyres, and basically the hot water built up in these gyres. You can see off the coast of Alaska, off the coast of British Columbia, off the coast of Southern California, Mexico, and so on. So it evolved and separated into 3 parts. So the heated water brings new ecology to these areas, even though it's just for 2 or 3 years. National Geographic, in fact, showcased this ecological damage and caused it a giant patch of warm water known as the blob shocks the Pacific in what some fear is a preview of our future oceans. But this is strictly a regional warming event due to Nishinoshima. So you have mass mortality of many marine life forms resulting from it. Sea surface temperature anomalies after multiple eruptions ended in June 2015 is shown here. So the Hunga eruption is shown in this red triangle. Hawaii, you have coral bleaching. the axial seamount, which is off the coast of Seattle, erupted from April to May 2015, and then Wolf eruption from May to June 2015 at the location where normally you have the El Nino, hot seawater. But you can see the timing is not Christmas time by any means. It is in June, July. Establishment of the very strong ENSO was during August, the end of August. You can see this heated water spreading across the normal region. But this is quite different from previous ENSO event, as in that you can also see the hot water further north in the North Pacific Ocean. Measurement of seawater temperatures here enable us to compare the ENSO event in 1997 to 1998 to the current one, which is 2015 to 2016. And you can see that the thickness of the heated water is much, much greater than during the 1997-1998. So you have to account for the differences, which is supported by observation records. This is based on the work of Zhang in 2017. Now, I've mentioned that there are impacts on Arctic sea ice as a result of these submarine eruptions, and this is shown in these charts. Normally, in the Northern Hemisphere, summer heating of the Arctic will lead to minimum sea ice in September. So I've shown here 2014, 2015, 2016 sea ice extent, which is the white area in these charts. Wintertime, temperature dropped, so winter onset, so the sea ice expanded. Based on the measurement of sea ice from the National Sea Ice Organization in the United States, the lowest record of sea ice was in 2012. 2014, 2015, 2016, when Nishinoshima was erupted, you have more gradual decline, but not as low as 2012. This led to our explanation. We have discovered the connection with submarine eruption. 2012, with the record low sea ice, was due to the El Hierro eruption in the North Atlantic. Shrinkage of sea ice is much greater in the North Atlantic as compared to 2014 to 2016. Shrinkage is much greater in the Bering Strait area. So if I go back to the previous slide, you can see it. 2014, 2015, 2016, the sea ice extent has shrunk much further near the Bering Strait, consistent with the heat source from the North Pacific block. If the heat source is from the North Atlantic, you would see much smaller, much faster sea ice retreat in the North Atlantic Ocean. The final thing that I'm going to talk about as an example of volcanic influence is sea levels in Hong Kong. Hong Kong tide gauges measuring sea levels are shown on this chart. We have 6 tide gauges. One of them is no longer in use. This is Chimawan tide gauge. It was discontinued. So we still have 6 tide gauges. The longest record in terms of tide gauge measurement is from North Point Quarry Bay. But why 2 locations? Because they have moved the tide gauge in 1986 from North Point to Quarry Bay due to the construction of the Eastern Corridor. So the engineers were concerned that it will affect the measurement, so they changed the location. Hong Kong Observatory was responsible for this record. What they have done is to draw a mean graph for this period of monitoring from 1954 all the way to the present. So these are annual mean in sea level. So they just took a mean graph line to represent the trend of sea level rise. And they come to conclusion. It's rising at a rate of 32 millimeters per decade every 10 years. But what have they missed out on this record? Now you can see that the record is not straightforward. It has in fact gone down a little bit, gone up very fast over this period from 1990 to 1999. Then the rise has disappeared. So if you look at the record in more detail, you can see all this. If you have good memory, you know the driest year on record is 1963. And you can actually see a low sea level point during the driest year. Why driest years are lower in sea level, you may ask? High pressure, little rainfall. The wettest year on record is 1997, based on the record of rainfall from 1884. So has this also got an influence on this rising sea level in this period, 1991 to 1999? More water discharge from the River Pearl into the Pearl River estuary may be responsible. More rainfall means lower pressure. Low pressure means higher sea level. So this seems to be consistent. So you can have other explanations coming in. But I think all of you can also see these arrows. 1959 to 1991, you have a 32-year pause in sea level rise. The highest point was 1959. Sea level has continues to drop. But then we have sudden acceleration from 1991 to 1999 in this location from Victoria Harbour, one location in Hong Kong only, a rise of 26 centimeter, which we can correct based on comparison to Typo Cow Station as absolutely not more than 17 centimeters. Then we have another pause in sea level rise from 1999 all the way to the present day, 23 years. So if CO2 is driving global warming, sea level rise, we don't see this in our record, right? The station have been moved, but they have shown it as a continuous record. So our conclusion in terms of sea level can be summarized in this table. There may be cyclic changes in sea levels that we don't know about. We all know the Chinese calendar has 60-year cycles, what is called the Atlantic multi-decadal oscillation. Can we see this? Crustal stability through loading and unloading, through tectonic movement, erosion, deposition. We are at the mouth of a delta. Sedimentation could cause crustal loading, causing it to subside. Rainfall effect, dry years, wet years, has to be taken into account. And then the accelerated sea level rise of 17 centimeter. And this is best explained by a professor from Florida. What is called the inflection point in marine seismic activity, which is shown in the previous chart with Terito. This is due to thermal expansion of the seawater in the oceans, causing this dramatic rise. So it's a temporary effect, and it's a cyclic change that we can see. Then we have the man-made impact. Hong Kong is an urbanly developed city with many high-rise buildings. Loading of the crust, surely we have some isostatic adjustment taking place. Reclamations also, landfills and so on. So the record in Hong Kong with the 60-year cycles is summarized here. Our record is basically too short. We have measurements from 1954 all the way to the present. So the record we see seems to be consistent with these 62-year cycles of Knudsen. So it has gone down and gone up slightly, but has gone down again. So it seems to be consistent with these causes that we have identified from the Victoria Harbour tide gauge. So to finish off, our main conclusions is shown here. Based on observation records, the selective volcanic eruptions studied and the current climate variability found are consistent with the timing, which cannot be explained by other means. I think the other things I've already said already, just a summary, but this PowerPoint can be made available to everyone who wants to read it in more detail. So volcanic eruptions as a cause in both cooling and warming is underestimated. It's part of our dynamic Earth. And I'll close with one cartoon slide by Joss in 2018. And what is interesting to fit in with the theme of this meeting, volcanic eruptions are a natural geodiversity experiment for us to learn from. So it leads to climate diversity, which is much more important than tourism, I think, if you ask me. I think the recent past is the key to the future. Thank you for your attention.
Are you saying that volcanism may have been a cause of Hurricane Sandy in 2012?
Yes, because of the hot surface seawater, but also, so it's the cyclones, tropical cyclones, frontal activity storms. Actually, there's an earlier case, the Suffren Hills eruption in 2010, that year, the same year, in the Caribbean, led to frontal activity storm hitting the island called Madeira. And afterwards, it hit Western France. I've written that up. That was published. We even have a weather chart of the volcanic cloud exacerbating the warm sector of the front. as it drifted towards Europe. So you can look at the satellite image to work back to the initial start of this volcanic eruption. So because hot air comes out from a subaerial eruption, and if it's in the warm sector of the frontal situation, it will exacerbate the temperature difference between the cold North Atlantic and the warm sector. So temperature is more extreme. So the frontal activity becomes even stronger. So Madeira that year had major landslides and fatalities much earlier that year than even Hurricane Sandy. I think I have a summary table of that year of what happened to the North Atlantic basin, including record temperatures and floods in different parts of Europe and North America. There's a succession of climatic events that we can track back to as a result of the temperature difference between land and sea.
Okay, how about this spike in UAH temperature data that's just shown up in the last few months? Do you think that's related to the volcano in 2022?
No. The best time for studying these volcanic eruptions is immediately afterwards, if we have satellite tracking. I have not kept up to date with all these eruptions. With the Tonga eruption, I think we can be very safe to start off with the first 2 months. And I usually don't work on the time up to the first 2 months. The first 2 months also include what is called the E-folding time of sulfur dioxide. That is quite interesting and important. Most volcanic eruptions release sulfur dioxide into the atmosphere, and if they're high enough, into the stratosphere. The E-folding time is the time it takes for the sulfur dioxide to be oxidized into sulfate, and this has solar radiation reduction impact. Usually, after 35 days, something interesting occurs. Based on the study of Pinatubo, people studying the E-folding time of the Pinatubo eruption in 1991. And I mentioned Chai 10 erupted in 1st of May, 2008. And 35 days afterwards, we have this worst rainstorm on record in Hong Kong, causing 2,400 landslides in a single rainstorm. It's quite dramatic. And the amount of rainfall coming down in 3-4 hours is quite a record. And the wettest June on record. I think the Tonga eruption, we have tracked the 35-day E-folding time, seems to point towards very heavy rainfall in parts of Indonesia. That's as far as we can tell.
Next question is it as simple that if there's high atmospheric pressure locally, that will affect the local, the sea level? It'll push it down?
Yes, I think the sea level elevation, it's well known that during typhoons in the Asian region, we have storm surges. So when we have low pressure system coming through, so we have elevated sea level, so low-lying areas tend to be flooded during the passage of these cyclones.
Is there an order of magnitude as to how much that local sea level can change just between very high pressure and very low pressure?
Yes. There's always a record of storm surges. If you look at the record available, based on tide gauges, we can have much more accurate measurements. So these are storm surge elevation, short-term ones.
Could it be half a meter or something locally between very high pressure and very low pressure?
Usually at least a meter or two.
All right. I did not know that.
I think in Hong Kong, our tidal range is only 2 to 3 meters. But during storm surges, it can go up to 6 meters. A difference of quite significant number. So this is why low-lying areas are flooded during storm surges, during the passage of a typhoon.
Yeah, I'm embarrassed to say that I did not know the storm surge is caused by the change in pressure, atmospheric pressure.
Yeah. This is what is called sighting, the Coriolis effect, depending on the coastal configuration. I think this is why when we have tide gauges, we have to do an analysis of the tide gauge. If we have 6 tide gauges within the area of Hong Kong, we can do a comparative study. So we understand what is going on at this 6 location. But if you have only 1 tide gauge with a long record, you assume this is the only good record you have. And this can be quite misleading. I think we're just fortunate to have 6 tide gauges in Hong Kong.
All right. On a separate note, have you looked into at all into the cause of this volcanic activity or try to predict volcanic activity 20 years out, anything like that?
I don't do any predictions. I basically studied observation records of volcanic clouds and of sea surface temperature. So looking at the record of observations, I don't do prediction.
Thank you very much for doing this. I hope to have you on the podcast again. Wyss Yim. Thank you.